So usually I start with defining the problems first. I think today I'm gonna skip this, as I hope you're all aware of the linear economy and the problems that they face, the externalities they cause, and the big damage that is actually done on environmental and also the society. I'll start right away, go into medias res with showing you the potential innovations that one can tap into by choosing the right path and looking into the whole system as such. I'll give you a brief insight of how a system can look like if it is defined around three strategic pathways. It's circular economy, it's nature-based, or nature-inspired if you want so. I can show you some examples of what's the difference maybe also. And participatory. Participation is key. If you want uptake of something, it's a co-creation process. Maybe you are aware of design thinking as methodology, and if you get a little broader, you can tap into systems thinking, which is also participatory, and something that has been externalized in all the system is part of the story. Alchimia Nova is now a group and has been founded actually in the year 2000 already. In 2010, the former head of institute died, and we had the chance to design the direction it goes, and went from pure phytochemistry to also phytotechnology and tapping into circular economy. If you're aware of circular economy, we are cradle-to-cradle partners since the year 2006. Cradle-to-cradle is like a design certification for circular economy. And if you see here, Bioversum was one side arm that we have now incorporated in the Alchimia Nova research. Now we have 3 entities in this group, and we work mostly in European projects in Austria and Greece. So our home base is in Austria, but we have another company in Greece as well. And we also have a non-profit research arm. In general, if you want to see one step ahead, if we want to look into nature and see how nature solves the problems, they have done this for 3.8 billion years already. So there needs to be something right in that system. Evolution proves to have solved many issues that we now again consider as problems in our system. So if we look into nature, we can find actually many solutions out there. Just by one single tree, you can explain how society works in total. It's one tree has the capability of applying so many different services into the same system. It gives shelter to animals. It provides fresh air, so it cleans, uptakes CO2 and provides oxygen at the same time. It cleans water, but also it can be an innovation source. In spring, a tree never tries to be more efficient. Never. It would always try to be as effective as possible. It tries to grow as many blossoms as possible, and it does not think, is this energy efficient or not? The thing is, once these blossoms are not pollinated and never become cherries or so in the end, the blossoms are nutrients for the same tree. They just fall down and become reabsorbed by the same tree. So just by leaving this picture with you, we can now extrapolate to many other human systems. We can design buildings to become trees, to have the same integrated ecosystem services or more services than just shelter. These trees can clean air, they can clean water, and they can provide habitats for other species as well. And if you look at in a whole, the same tree buildings, more of them in a bit built in a city, is like a forest. It becomes an ecosystem. So cities become ecosystems. So we use, now these are very green, and we use plants for doing most of the work in these buildings. It's not that the technological solutions are not out there, but we prefer to use nature-based solutions. And we work with plants as our superheroes. We would have these superheroes also in our educational material. They can uptake metals, they can clean the water, and do many other amazing stuff. So these are our workers for us. So there are many different possibilities. You see, this is like a green wall that we have applied in several like hotels and homes, and this cleans the water from the same building. Wastewater enters these green walls and clean water comes out and can be reused in the buildings. The good thing is with the green wall, putting it in a vertical space is the space arrangements. You don't need to, you can otherwise do just a vertical or just a horizontal wetland as well. This is just a vertical wetland. And we have now developed more systems going into, is this a laser pointer? Yeah. Going in facade structures. This is a facade structure for winter applications with semi-permeable photovoltaics in the front. This is like an indoor wooden casing. This is a facade prototype. This is actually made of more than 70% of construction and demolition waste. And this is an air treatment unit for cleaning the air inside buildings and humidifying, which is also a need during the heating period, which is quite long, I suppose, here as well. But if you then go the next step, we build now plant-based urinals. So far, unisex, the first unisex toilet for public use. It's potentially also mobile. It's super self-sufficient. You don't need access to wastewater or fresh water or energy. So it's off the grid, and it's up to 300 uses per day. That's the design, and we now build it and demonstrate it in Vienna and several places, and we've already found many interested other cities, municipalities that would like to test it for events or just inside the city. It's greening the city, plus it's serving the function, the additional function. If you now extrapolate this mindset and go to full systems, we can do much more water cycles on a bigger scale. That's a project, Horizon 2020 project for Greece. That's one of my favorite projects, actually. It's, besides that we designed it, it's also salt water is treated just by solar desalination, and we can recover salt, tropical fruits because of the high humidity and the high temperatures, and sweet water. We use the wastewater in these systems, in these islands especially. This is in Greek islands, Mykonos, Lesbos, and Tinos, and they have a high water scarcity. In the summer, high tourism, less water available, and then they need to ship water from mainland Greece to these islands. This is the same for many of the islands if they have not natural rain capturing systems and the like. Rain capturing, I just said it. There is rain capturing here as well, aquifer recharge, and also here in some other like underground rainwater capturing, because there's it's otherwise it would evaporate. But going back to the main system, here's wastewater generated, the carbon stored in the wastewater. Human feces has still some carbon. It's just actually the sun energy metabolized in our system. The plants take up the sun energy, nothing more than that. We eat it, and we can't make use of all of it, and we just get rid of it, and we can make use of this carbon and the sun energy stored in it in biogas systems. So far, we treat the water and we get it back to the field. And this field is restorative agriculture, as it's called. So restore ecosystems by applying this setting. This is like a permaculture field, and will be, imagine these Greek islands, super dusty, rocky, and then we will have a hill that is greened suddenly, and it's like an oasis. And greens have all these additional effects of cooling climates and humidity and much more. And we can capture humidity also by condensation, which is a little tricky physical-wise, but there are some very good tricks on how to make use of cold seawater and stuff for condensations. We can also do the same scenario, and we show this now in buildings. So we have now 300 units. The last project was with 300 in the winter and 3,000 in the summer, and this is just for several, up to 20. We now show it for 70 and 20 persons around that range in Spain and in Austria. How we can have small energy, water, and nutrient cycles inside these buildings. Here, we collect again wastewater from the building. We don't need to re-establish piping systems. There's no grey water separation. It's done all underneath or besides where the wastewater discharge is usually happening. And there we have a solid liquid separator which works passively. And the solids again go to biogas. Biogas can be used inside the building, or if the unit is big enough, also for coupling it with energy. And the liquid part is again treated in these green facades and then used in urban farming setups. For the building itself, the materials, there are 11 solutions. The materials are also looked into, and they are through building information modeling captured and then known where to find which materials when they are dismantled. Usually you demolish them, but in this case now it's seen that they are actually storing materials during the lifetime of the building. So it's a biological cycle representing and the technical cycle. For the building materials I can talk you through a whole session, but it goes a little far. You have this service mindset that you don't actually buy the windows or buy the materials, but just use the service of those. If you go to a municipal level now, and you look into the wastewater, now we have just used biogas so far. But the next step would be to not actually crack down the longer molecules that are available in plants, but use them as they are, or use them in a bigger scale and actually have higher value addition to the systems. So you could make use of wastewater and or the organic fraction from the municipal solid waste and make, in the end, building materials. Where is it here for construction? You can make, of course, fertilizer, as very often shown. You can make PHA from, these are purple organisms that would feed on wastewater and would provide you with these bioplastics, and of course, it's not of course, but it's also cosmetics that you can work with. It's an extraction process of ectoine. Maybe the cosmetic persons of you understand, know about this molecule as well. Yeah, that's a municipal level, and the idea is very much going into having a set of different biorefineries, or as I've shown you before, the building might be a converter of nutrients inside the building, and now the municipal level you can have the biorefinery thinking, or you can also have them in smaller units. And one company in Spain is actually working on doing this in smaller units, and this is a very interesting decentralized scaling. They just provide you with containers. These might be 30 persons organic waste. They produce the PHA, the bioplastics, inside these containers and just extract the plastics from these containers. And it's very, they're located here and there and then in other places around the city. And they said they can decrease the costs of making bioplastics by another 50%. Having this in mind now, how this system can be more decentralized, we can actually even find of of a way how to spread it in a city. Besides that, the system is a little in crisis. We harvest, mine, process, and then put it through our system and just discard it and say it's actually waste. We can have a more regenerative system and collect in different areas of the city the waste streams and metabolize them or convert them to become the new sources for the same system. So this is like a take and give. These hubs, we call them resource metabolization hubs or resource conversion hubs. They can become innovation spaces of a city or of a region or of a village or whatsoever, and can offer many more services to the customers, to like the citizens. They can offer repair services. They can do all sorts of things. That's the like cities of the future. Well, now, this is more or less a similar graphic than the ones before, but I want to show you also this arm, the carbon dioxide uptake and the biosynthetic capabilities of plants that go into these fine chemicals. As said, we split down these biosynthetic pathways, and now we want to make use of the biomass as is. These regenerative cycles. That's the biomass cycle, and it's actually a very sustainable one, as you know. And if we now look into the biorefineries, how this will develop in the next years. Where is it? If we now look into the system, how the system changes. If the system changes and everything that is now deriving from petrol. I don't know if we are even aware of what is derived from petrol, but it's actually anything we would use. It's varnishes, it's like finishings of wood, it's the glue that is used in the wood, is the colors, is the pharmaceuticals, is the soaps, you name it. Everything is derived from petrochemistry. But there might be some changes due in some years' time, and it's all will be responsive for just biorefinery. So petrochemistry will decline. Is it 20 years? Is it 50 years? It doesn't really matter. A fact is that we will need to rely more and more on biomass. And then do all these same products that we are now used to live in colors, whatever it is, from biomass. That's a fact. There are some pathways that are maybe more valuable and maybe less valuable despite the cost of the material. So now what we do a lot, we have wood. You here in Latvia, you work a lot with wood, in Austria as well. So it's the forest industry. And it's actually, if you burn wood, you have a very high value material and you have a very low cost application. So I doubt that this is the cleverest way to work with biomass. If we now look into something that we call biocascading, we use these fine chemicals and don't break apart the molecules. As said, this is the plant builds up these high value molecules, and usually even in biorefineries they break them down, and you can imagine these have high value, and now you reduce them to low value. In case of burning, is the lowest value possible, is CO2 again. It's just another conversion process, nothing else. But if we use these high value molecules as they are, we actually recover more value. And it's just another way of thinking in the circular economy. Circular economy is about value and value recovery at the highest possible stage. If you follow this guideline, it's this what is on spot for all of the applications. So biorefinement is without breaking things, and I'll tell you now, I'll guide you through three brief examples that we have worked on. This was actually a project that we have worked on for many years, and that it's finally reached the market, and we found the new young guys that really are behind the story and go for it. It's the fruit kernel cascade. So it's actually a residue in the like marmalade or juice producing or so from the industry, and we use these kernels, crack them open, and have then this soft kernel, which is like an almond. In our case, it's just the kernel of apricots or plums or peaches, cherries, all sorts of things. And we diverted these two materials. Actually, there are more than two. There are three. There is this one. There is this hull, and then there is the soft kernel. So we use this for non-food applications, abrasive, fumigant, and then even for dental abrasives is working. We used it for cosmetics, and it's working perfectly. It's not only the oil that is pressed from the soft kernel that's working. You can also have a peeling function if you mix it with some of the hard shells. But also for food applications. There is a famous chocolatier in Austria. He's called Zotter. He's like organic, fair trade, and all these things, and does crazy chocolates with all sorts of things like fish skins and you name it. And we have developed some very nice, good tasting products with him based on, marzipan. Now it's persipan, cherry pan, prunipan, and all these pans. It's the same thing, but it has a slightly different nuance. And the oils are also quite in this direction. They are very rich, they are very good, tasty, and they remind you a scent of the fruit. And that's like fascinating. You smell the fruit in the oil. And they are different oils, of course. And of course, the press cake usually is fed to whatever sort of cattle also, or animal husbandries. Used in animal husbandry, but you can also use it in muesli bars. We make some yogurts with the press cake and muesli mixtures. For wine and olives, we have done the same application. We have not gone through until commercialization. This is still more in the concept phase, and it's applied to a certain extent. There is a lot of pruning in both of the systems. And there's then, of course, there's pomace, and there's also lea from the winemaking process. And all of these you can make use of and create additional value. There are very good high value antioxidants in the stems from the vineyard, for example, or resveratrol for the experts of you. And you can also find oleuropein, which is another high super antioxidant, in the olive prunings. So we did an analysis, and this is true for everything. Now, seeing again biodiversity functions, we always work with intercrops to stabilize or increase the resiliency of the ecosystem as well. And you can use now all sorts of things in this integrated biorefinement. Extracting high-value chemicals and then go to more bulk value. I'll give you some hints in a bit how we design a concept like that. So high value, you see, this is maybe for some of the experts, cosmetics, nutraceuticals, essential oils. We have been talking a lot these days. But also intermediate value things, oils, animal feed, and the like. And of course, also tapping into fertilizers and agri-foods. So everything is possible in the field. You just need to find the right balance between what is done locally and what is done centrally. The bigger the unit, or the lower the value, let's put it that way, the lower the value of the end product, the bigger the unit usually needs to get. So that's also something you have to keep in mind. If you have very high value, you can even have a kitchen scale biorefinement. You could just cook and you can still sell the product and have can actually recover the value. If you want to go into energy production, it's usually you need bigger units. Except there are some exceptions if you have everything available in a like 20 kilometers range and so on. Usually you lose the value for burning, I think it's around 20 kilometers. If you go more than 20 kilometers, then it's usually not worthwhile for energy recovery. But now, looking into this super resource of yours that, or you can create many more things from wood as feedstock source, besides fuels or building materials, which is quite common. You can also do the pharmaceuticals from forestry residues. Actually, in where the branches in the wood that are usually not wanted, from the chemical perspective, that's the most interesting thing. They would keep like high antioxidants and make it really strong, the wood, that the branch does not break there, and these can be used and extracted potentially. There are these needles from all the spruces and pines that have high value compounds, not only essential oils, but also the wax could be used from this protection layer. So you could actually use much more of the system. Now, I told you about this decentralized and centralized biorefineries, and I talked to you about forestry residues. Now, this is one of the aspects, forest, right? There's much more. Agriculture, and this is all, if you see the residue streams, which is the gray one, goes now to local biorefineries. They are treated, value is recovered, and then, or like a pre-treatment process, and then intermediate products are shipped to a more central biorefinery where you go for bulk products. And all of these systems can serve the humans for their purposes. So with all this background knowledge now, with colorants, antioxidants, and so this can all be done in these systems actually. What is important, usually a certain quantity of the nutrients are left on the field on purpose, which is very important for the natural ecosystem to work. So if you now take more from the field, for example, straw or you name it, you always need to be sure that you return nutrients back. So that's very important. And now working in this biocycles thinking, there are two aspects that I want to share from this very intensive project with you. One of them is the non-readable chemistry part. We looked into how we can actually substitute the chemistry and substitute them with all sorts of bio-based materials. This is glucose, and these are all like certain end products. If you want, you can look it up, this diagram, and you can zoom in wherever you want. It's a very fancy, very nice tool. And these are the secondary products, sources. And this is how these secondary products like interlink with the normal chemistry of things. That's now, it doesn't need you to read anything. It's quite a complex thing. But if you're interested in the chemistry, let's say we have solved it, or if we have solved. Yes, thank you. This is the one side. It's the chemistry. We looked into TRL and the biorefineries, how the conversion ratios, and then the land use, and so on. We will have soon an executive summary of the next report for the Austrian ministries ready to download. This is the Biobased Substitution for raw materials. This is the old report. This is already online, and the newer one will come soon, where we look into the residues. The other side of the story is the treatment chains, how they can connect with each other, and there's the logistics behind the story. That's Austria, and we did a model from the logistics department from Austrian University of Life Sciences. They worked on this is straw. These are straw fields. And how these straw fields can field into a certain area. We looked into underutilized infrastructures that are like old mills or like sugar refineries that are not more in use. and we looked into the systems where they are accessible and where to find the spots, have this pre-treatment done in a certain area, and then have a centralized system. That's like Vienna here. There is also some underutilized infrastructure. That's like a mathematical model, algorithms that calculate the system, but that's where it needs to go, and that's now for the ministry to know how to make the future investments and where to go in which direction. So, to sum up, we see waste as our nutrients, and systems can be designed to be used for this resource recovery and like never-ending resource loops. Waste equals food is one of our things. And the major thing, we have the technologies in place. We know about the technologies. But one of the major things is not the technologies, but it's the social transformation that is needed. That these systems, these visionary things can be really applied into our systems. Eat poo. That's like, that's a more a social thing than a technology thing. And I want to leave you with that and encourage you to share the visions and get active and implement things. Thank you.